Right, good afternoon. So we have Chris Fonnesbeck here from Vanderbilt University, I think, and he's going to talk to you about probability, which will provide you lots of room for a nap. Or something exciting will happen. Who knows? That's right.
All right. Okay, welcome everyone. As I was introduced, I come from Nashville, Tennessee, or at least I live there, in the Department of Biostatistics at the Vandy Medical Center. So I'm going to talk about probabilistic programming, and I'll begin by defining it. Probabilistic programming is not new. The term is new. It's one of those things that we've been doing for quite a while, kind of like data science. It just has a new name now. Probabilistic programming is any language that's used to describe and fit probability models. It has nothing to do with code being randomly generated or anything like that. It's for probability modeling. So to illustrate, one of the characteristics of a probabilistic programming language is that it has language primitives that are stochastic. So they have random qualities to it. So for example, we may want to define a distribution over some various values of a variable x, and instead of assigning a single value to it, we assign a probability distribution. So here it's a normal distribution with some mean mu and standard deviation sigma, and it's got a method, for example, that will draw random values. In this case, 100 of them, and assign that to a variable. You can get more complicated than that. You can have distributions over functions, where each realization, each random sample is an entire function, not just a value. And importantly, what we're able to do is condition variables based on others. So we might say that some variable p, a probability, is beta distributed. Don't worry about it if you don't know what that is. It's just a different probability distribution. And then we're going to use that to condition the value of another random variable, in this case, a Bernoulli. And what this does is it allows us to specify probability models at a very high level. What we use PP for is it allows us to, well, it facilitates the application of Bayesian methods. And that's an area of high interest amongst statisticians and others. And the thing about Bayesian inference is that it interprets probabilities a little bit differently than classical statistics. And in particular, it uses a definition of probability that's known as inverse probability. And it's inverse because it reasons backwards from effects to causes. So we may have observations, y, data, things that we observe. Those are the effects. And we can use those quantities in conditioning statements to help determine what the causes might be. So the bar is a conditioning operator. And the theta can be some vector of parameters that we might be interested in. So why do we need a whole other paradigm of statistics? Well, there are a lot of very good reasons for this. The one that I like the best is that it's a pragmatic justification. It allows me to build really complex, well, more importantly, very realistic models of things. So I'm an epidemiologist. I build disease models. And Bayes offers me a lot of flexibility. And that flexibility is partly because of this simplicity and this ability to break down big models into small conditional pieces. So here's Bayes' formula. This is the only estimator that you need if you're a Bayesian. And the thing about it is that it uses probability distributions to characterize what we know or don't know about some unknown quantity or quantities that we care about. And so at the far end, we have a prior probability that essentially encapsulates all the information that we know about our unknowns before we observe the world or do an experiment. And then we take data that we observe and we update that prior probability to what we call a posterior. And it's called posterior because it's after you've observed the data, and that's why we condition on y. And the nice thing is that the outputs from probabilistic programs are always going to be in probabilistic terms. And so you don't just get a single value, a single point estimate, or a single prediction. You get an entire distribution of them. And what that allows us to do is provide measures of uncertainty associated with those estimates. It allows us to ask questions like, what's the probability that the true value is bigger than 0 or bigger than some other value of interest? So that's what it is. How do we do it? There's 3 easy steps to probabilistic programming. The first is encode a probability model. Specify a probability model in any language you like, as long as it's Python. How do we do that? Well, first, we specify our priors. So again, this is quantifying the uncertainty in our latent variables. And so we might pick, say if we have something that we know the values are somewhere on either side of 0, we might pick this is a standard normal with a mean 0 and a variance of 1. You've probably seen normal distributions before. You might not have seen this one, though. This is a normal distribution, too, that line across the bottom. This is a normal with mean 0 and standard deviation 100. So this is encoding lack of information. We don't have really any preference almost on the whole real line in terms of what value it's supposed to be. If I'm trying to estimate, say, the prevalence of a rare disease, I might pick something like this, where the probability is piled up close to 0, somewhere less than 0.1. If you're a geneticist, how many people have done fruit fly breeding experiments as an undergraduate in biology? Anybody? A couple people? If I close my eyes, I can still smell the ether from that. And so let's say we're doing breeding experiments and we want to measure, let's say, the variation in fly wing widths. Well, we wouldn't put a big normal prior on that. We know that wing fly widths can only vary so much. And so we might pick a little log normal distribution like that. Let's say we're a sabermetrician or we're just a baseball fan and our favorite player has just started the season by going 4 for 10, 4 hits and 10 at-bats, and we want to know the probability that he's going to maintain that 400 batting average for the rest of the season. Well, the distribution I've shown here is based on all of the batters in Major League Baseball going back as far as you like in history, and it turns out to be a mean of about 0.26 with a standard deviation of about 0.03. That's what we should be using as our prior because we know how baseball players perform. Next is the likelihood function. The likelihood function is basically our data generating mechanism, and it conditions on our model on the observed data. It's how we update that prior probability. So these might be things like a normal distribution. Let's say we're studying outcomes in terms of height and weight of patients. Those tend to be normally distributed. If we're doing our baseball example, a binomial distribution describes the number of hits in n at-bats based on some probability of getting a hit. If you're doing web analytics and you want to know how many people, or you want to model how many people are visiting your website every month, year, day, you might use a Poisson distribution for modeling counts, that sort of thing. Next step is we want to infer the values for our latent variables, the posterior distributions. And it seems pretty straightforward. We update our prior distribution with our likelihood to get a posterior, but this is an unnormalized form here. We're forgetting one little piece, which is this marginal likelihood, or what's called the model evidence. It's really just a normalizing factor. But when you figure out what it is, it turns out that it's the numerator integrated over all of theta. We're going to integrate out theta. And that's fine if we only have, say, 1 or 2 parameters. Some of us can do integration pretty easily with a couple of variables, but if you've got 10, 100, 1,000, million parameters, it's not possible to do that. And so we require numerical methods. And one of the things that probabilistic programming does is it allows us to abstract that inference procedure. And that's all I'm going to say about it right now. I'm going to circle back to it later, but we're going to consider it a black box from a probabilistic programming perspective. And then the last step that people often overlook is you have to check your model. The model outputs, the validity of them are conditional on the specification of your model. And you specify your model based on a whole bunch of assumptions that are largely unverifiable. So you've got to go back in and check the model. Are the results reasonable? One nice way of doing that is to actually simulate data from your model and compare that simulated data to the model, or the data that was used to fit the model. And you can see, in this case, they line up quite nicely. These could have been drawn from the model that we've used. So, like I said, probabilistic programming is not new. Statisticians have been doing probabilistic programming since the grunge era. So in the kind of the early 90s, a package called WinBugs came along from the folks at the University College of London, and it was great. It exposed Bayesian methods to thousands of people, statisticians, applied scientists who never would have been able to do Bayes if they had to code it by hand. And it featured a probabilistic programming language, the bugs language, that allows you to specify variables, distributions, functions of distributions, and nowhere in here do you have to say how you fit the model. Bugs would do that for you. It uses MCMC. But after using that myself for quite some time, started sort of become frustrated with it. For one, it was closed source, and even when they did open up the source code, it's implemented in Object Pascal, so there weren't very many opportunities for me to contribute. And really, I don't want to specify my models using some crappy domain-specific language. I want to use Python. So when I was a graduate student, I started hacking away at some Python code for doing probabilistic programming, or Bayesian inference. And at the time, I didn't expect anybody to use it other than me, which explains its atrocious lack of quality. But over the years, as I put this on initially SourceForge and now GitHub, it's attracted some really talented developers, people who are much better at this than I am. And the current version of PyMC3 is now based on Theano, which I'll describe in a minute. And this allows us to implement what we might call next-generation Bayesian approximation procedures. And actually, as of late last year, we're now under the NumFocus umbrella, so we're really happy about that. It's already reaping benefits for us. Theano is a Python library, or at least it's got a Python API for specifying and evaluating mathematical expressions using tensors, which are generalizations of multidimensional arrays. And it comes out of Yoshua Bengio's LISA lab. It's now called the Montreal Institute for Learning Algorithms. And what it does, it performs dynamic C code generation. So it makes all this stuff very fast. And importantly for us, what it does is that it does very efficient automatic symbolic differentiation. So for any model you throw at it, you can get automatic gradients. And this is a boon because we'll need them. So to motivate, show you how we implement a model in PyMC3. I'm going to motivate that using a real example. This is a example using radon gas contamination. Radon gas is a radioactive, odorless, tasteless gas that is actually the primary non-smoking cause of lung cancer. And it gets into people's houses through the groundwater and through cracks in the soil and the bedrock. And prolonged exposure increases your risk of cancer. And so the data we've got here is some monitoring data from households in the state of Minnesota from different counties across the state. And we're going to try to estimate the probability of a house being contaminated, or the levels of contamination in various places around that state. And so specify our model here. What we're going to do is just use a very simple one. It's going to have mean values for each county individually. And then there's an effect of having a basement in your house. If you have a basement, you have a higher probability generally, or it's expected, of having radon contamination because it's easier for it to get up into the house. And then the error term there is essentially the distribution of our data that represents measurement error or temporal within-house variation or between-house variation, that sort of thing. So what we do in PyMC is we instantiate this model object. And this model object can be used in conjunction with a context manager. And what that will do is that when we start specifying variables for our priors and our likelihood, it will automatically add them to the model. So we have to have add statements and so on. And what we see here are what we call some stochastic nodes. These are the variables in the model we don't know the true values of. So the county-specific means, and the effect of basements, and then there's the error term there, the error variation. And because we're using Python 3, we can use fancy Greek Unicode characters for our variables. So if we introspect some of these guys, so we look at beta, and its type is this free random variable in PyMC3, and it's got very useful attributes. It can calculate the log probability of any value that you pass to it. And because this is a tensor a Theano tensor. It's evaluated lazily here. And then we can sample from it. We can draw random samples from that distribution as well. Next step is we specify essentially our regression function here, right? This is a linear combination of the data. Then we get an expected value for every county with or without a basement. And then our likelihood is just another distribution, a normal distribution in this case. But here we add this additional argument, says observed, and that's where we pass our data in. Okay, so we've developed this graph, essentially, a directed acyclic graph, and it's in Theano, and we're good to go. So now, I kind of glazed over the whole posterior calculation, just told you it was hard. It's analytically impossible. It's numerically challenging. So how do we do it? We're supposed to, not worry our pretty little heads about it. Just let probabilistic programming take care of it. But it sort of reminds you of the South Park underwear gnomes, right? Where they have a business plan to collect underwear and profit from it, but they're missing the key step in there. Well, similarly here, I've kind of set up the same sort of thing. How do we get this inference if we have to do impossible calculations? And what we have to rely on are approximations of one sort or another. And over the years, different approaches have been established for that. And they range from, at the very top, brute force maximization of the unnormalized posterior. So you'll get a modal value, but you're not going to get any sort of uncertainty around it. It's not a fully Bayesian approach. The second one, you might do a normal approximation. So assume the posteriors are normal, which can be fine unless you've got some skewness or some covariance between them, and then it becomes a less realistic approach. And then a variety of sampling-based approaches that folks have used, and their adequacy kind of depends on your model and on the objectives of what you're doing. The de facto standard for doing Bayesian inference is something called Markov chain Monte Carlo. Now, while we're not able to sample independently from our posterior, because we don't know exactly what it is, we can sample in a dependent fashion. That's what MCMC does. It creates a Markov chain. So Markov chain is just a sequence of variables whose next value depends on the value partly of the current element in the chain. And if it has satisfies certain criteria, its distribution will be indistinguishable from the posterior distribution of interest. And in particular, it's going to satisfy this thing called the detailed balance equation. If you do that, you can do MCMC and you can get a reasonably good approximation of your posterior. And the workhorse of this class is something called the Metropolis algorithm. Actually, I think our next speaker is going to talk about Metropolis a fair bit, so I'm going to punt on explaining that in great detail. But you're essentially proposing values, and you have some sort of function to either accept or reject it. If you accept it, you add that proposed value to your sample. Otherwise, you retain the current value. And it works fine in a lot of cases, but where you have sort of larger models, it can perform poorly. It can have trouble converging. So we're trying to get samples from this oval here, and you're seeing, the samples are kind of uneven. It kind of stops from time to time, and that means that it's getting its proposals rejected, and so it's retaining that current value. And you often require tens or hundreds or even hundreds of thousands of samples, even more, to get a converging algorithm. And it's very inefficient. Its optimal acceptance rate is about 24%. So a newer so that would be what I call kind of first generation MCMC. The next generation uses a much better approach in the sense that we abandon this random walk behavior and we allow ourselves to make proposals that are more likely to be accepted. And we do this by using gradient information. We talked about Theano providing us gradients. It's required to do this sort of thing. This is called Hamiltonian Monte Carlo. We're essentially simulating a physical system, the Hamiltonian set of equations, where we have a frictionless particle or like a marble rolling around on the manifold that is our posterior distribution. So no more random walk. So we essentially flick our marble across the landscape and calculate a whole bunch of what we call leapfrog steps that discretizes this continuous system, and then you accept a value at the far end. So it allows you to go clear across the model, doesn't get as many of those points rejected, and so you get something like this that makes long, confident jumps that are usually accepted because, again, it knows something about the gradient of the model. And your sample ends up being pretty close to what you'd get if you were able to independently sample. And the one that PyMC uses is an extension of nuts that sort of, extension of HMC called nuts, the no U-turn sampler, that essentially auto-tunes a lot of the hyperparameters. And so in PyMC, it kind of looks like this. You call sample on your model inside your context manager, and it will draw 1,000 or so is all you need for this one. And initially, it will try to initialize that algorithm using something called ADVI that I'm going to talk about in a second. And it runs pretty quickly, and so you get some nice posterior samples here that you can summarize. And so for our Radon example, you get estimates like this. The dots are the data. The blue lines are the county-specific estimates, and the red is the overall mean. So we would do model checking on this. We would find actually this is not a great model. It actually overfits. It's overfitting the ones with relatively little data. So we would go back and fit something better, like a hierarchical model. Another approach that you can use, the other sort of next generation tool that we have at our disposal, is something called variational inference. So even with those more sophisticated algorithms, MCMC can be quite slow when you have big data. And we're in the era of big data now, right? Everybody has bigger data sets that they want to fit. You really can't use MCMC of any kind with even moderately large data sets. So another approach is to take some approximate unknown or some approximate known distribution and use that to approximate our unknown posterior. And what we do is we transform that known form and parameterize it such that it's as close as possible to the true distribution. And what this does is it changes our approach from that of a sampling-based approach to an optimization approach. We can just do straightforward optimization, Nelder-Mead, that kind of thing that we know how to do that's fast. The way that we measure closeness is based on something called Kullback-Leibler divergence. It's an information distance, essentially, between distributions. And this is the form here. But you can see that our posterior is in this function, and so we don't know what that is. So we can't optimize it directly, but it turns out that minimizing Kullback-Leibler divergence is equivalent to maximizing this piece in the middle here called the evidence lower bound. So if we maximize that, we minimize Kullback-Leibler distance. And that's great, but again, this has been around for a while, but it's sort of very manual. You got to go in and specify what your approximating distribution is. You got to make sure that it supports all the potential values of the variable that you're trying to approximate. But very recently, there's a great paper by Alp Kesselbier and colleagues that essentially automated this using something called automatic differentiation variational inference. And what this does is it chooses the approximation for you, and then does a transformation so that all of the requirements are satisfied. And then all you have to do is hit the button and optimize. And so what we get is something like this. These are not samples. This is the mean evidence lower bound. You can see that it hits this asymptote, so it converges on something. And that something depends on what it is. So here's a contrived example using a known true posterior, a beta 147, 255, and that's the dotted one. And you can see for various numbers of optimization iterations, you get quite a good posterior approximation after a while. And so in PyMC, we've got this implemented as a fit function. So we had sample before, now we have fit, and it will go in and run the optimization, and we get this approximation object. And since this is a known distribution, we can sample from this independently and get a sample just like we would with an MCMC approach. And your mileage may vary. These are approximations. The trade-off is you can get an answer for large data sets in relatively short period of time. The good news is that the approximations are getting better and better. We're getting better and better versions of these algorithms, and we're starting to implement these in PyMC3. There's a whole bunch of new stuff. This used to be sort of a three-man show, PyMC, but we've taken on lots of new developers in the past few years. We've got some really nice stuff. Gaussian processes, due largely to Bill, who's sitting here in the audience. Elliptical slice sampling, another MCMC algorithm. Sequential Monte Carlo, time series models. We can do some really neat things. For example, we can interact with packages like Keras for doing machine learning. Keras allows us, actually uses a Theano backend as well, optionally. And in this case, we're implementing a convolutional variational autoencoder as part of a PyMC model. So we can define this class here and pop it right in to our model. And what we're doing in PyMC then is adding basically priors on the unknowns, right? So we have these latent variables, the z's, and we have the observations x. That's the likelihood, and then we drop this convolutional neural net essentially in the middle as the decoder, and it runs. Thomas, one of our other key developers, implemented Bayesian deep learning in PyMC3. And again, all this involves is, if you're familiar with deep learning and neural networks, is we put priors on the weights, essentially, of the neural network. And we can fit that using MCMC or variational inference. And what we have here, that actually is a picture not of classification probabilities, but the standard deviation of them. So we can get uncertainty associated with our predictions from our neural network, which is great. The future is bright. We're getting lots of new stuff, pull requests for really interesting new stuff. Operator variational inference is one of these newer approaches for doing variational inference that has sort of better approximation performance. Similarly, things like normalizing flows. Riemannian manifold HMC, it's a souped up version of HMC that uses not only gradient information, but second order derivatives to get even better proposals. Stein variational gradient descent, ODE solvers. And this year, we're happy to announce that we have 3 Google Summer of Code students that are going to be contributing as well, so we're excited about that. If you're interested in exploring some of this stuff, one of the best places to go is actually on GitHub. We have a folder of notebooks, and we've had amazing contributions from both our own developers and others who aren't part of the development team, and they've contributed a whole slew of amazing models, well documented, well explained in the form of Jupyter notebooks. If you want to know more about probabilistic programming in the context of PyMC and Python, Cam Davidson-Pilon put together a really good book years ago that uses a computational approach to give folks an intuition about probabilistic programming, and it's based on PyMC, and it was just recently updated by the aforementioned Thomas Vicky and Max Margenot from Quantopian, their employer, and they ported all of this to PyMC3, so this has all been updated for PyMC3. So finally, I'd just like to acknowledge the rest of the PyMC3 team. Most of these folks have only jumped on board in the past year to 18 months, so it's been really fantastic. It's really hard to keep up with the progress of the package. And I encourage you to not only try out some of these things, but if you're interested and capable, please do contribute. We would love to diversify even further and really hit it out of the park doing probabilistic programming in Python. And I think I'm out of time, so you can't ask me any hard questions, but feel free to approach me after the talk. So. We have time for one. I shouldn't have deleted those slides.
Just a general question in doing Bayesian analysis. How would you suggest going about selecting your prior? I know that in a lot of applications, there's really a lot of different ways you can reasonably set priors. Mm-hmm. Is that something that you think about tuning, or what is like the optimal? How do you go about defending your choice of what the prior is? Because you're in my experience, like your end results are somewhat sensitive to how you set your priors.
Could be. That's a good question, and my tutorial spent a lot of time. I did a tutorial earlier in the week on this, and we spent a great deal of time going over that. Like every other part of your model, priors are a choice that you make, just like what data to collect, which likelihoods to use. But you have to be explicit about it. You can't hide your priors. And the best thing you want to do is do a sensitivity analysis. So it's not tuning so much. It's just making sure or quantifying to what degree your inferences are sensitive to your priors. And so you can, either change the functional form, use a gamma instead of a normal, or log normal instead of a normal, or change the amount of variance you give it, the amount of information. And if it's relatively insensitive, you're good to go. If they're sensitive, then you've got some explaining to do. But so just like any other part of the model, you got to kind of validate it.
Hi, I hear you don't like crappy DSLs. What do you think of Stan?
Oh, no, Stan is a Turing complete language. No, Stan is great, and we interact well with the Stan team. Stan, for those that don't know, it's kind of the successor to WinBugs. So it's from Andrew Gelman's group at Columbia, and it's an expansion of the Bugs language, and again uses these sort of newer MCMC samplers and variational inference. And it's excellent. It's actually a C++ library now, which is better too. So anything you can build in PyMC, you can also build in Stan, and vice versa.
Thank you very much.